Hello students, how you doing today? I'm Mr. Elliott, and let's go ahead and get straight into our lesson, shall we? Happy Wednesday. I hope you had a great time sleeping in this morning as Mr. Elliott was at work trying to be the best math teacher I could. And once again, I apologize for the retraction I had to do today. Elliott hates making mistakes, but it happens. Today's topic, it is part 3 of our solving systems of equations lesson. Today we are solving systems of equations using elimination technique. Now I call it elimination technique because that's how I learned it. Some math books call it the adding and subtracting technique. It's all the same and it's a good technique. Come on in, grab that paper out of the printer. Okay, our first example we're going to do here is x plus 3y equals 6 and 5x minus 3y equals 12. Now this problem is custom built for elimination or addition. I personally don't use subtraction, but in elimination what you essentially want to do is add the two equations together and get one of the variables to cancel out. And we can do that right now with this particular problem. And if we look right here, you have a positive 3y, a negative 3y. So if we add the two equations together right now, 1x plus 5x is 6x. Positive 3y minus 3y, well that's equal to 0y. Where can I write this? And 0y, and that's 0, 0y is 0 times y. Well, that's just 0. So we don't put anything here at all because 3y minus 3y is 0, just straight up 0. So I do not include the y's at this point. The y's have been eliminated, and 6 plus 12 is 18. And now we just have a simple one-step equation. Divide both sides by 6, x must be 3. And then second step is the same as the second step was yesterday, or the last step. We're going to take x equals 3 and we're going to plug it into either one of these two equations. When I look through these two equations, this one looks to be a little bit easier to deal with. So it's good form to write out the entire equation first. Good form. Then we do our substitution. Everywhere we see an x, we plug in 3. So 3 plus 3y equals 6. This becomes 3y equals 3, which becomes y equals 1. And then don't forget to answer the question at the end, writing as a coordinate. So our answer was 3, 1. That was example 1. Now example 2 is going to be, what if one of these two equations, like what if you can't add the two equations right now and get a variable to cancel out. So I have negative 2x plus y equals 5, or x minus 3y equals negative 30. Now if I try to add the two equations together right now, nothing is going to cancel out. 2x plus x will not cancel out. Y plus negative 3y, the y won't cancel out. So what we have to do is we have to multiply one or both of these equations by a number to set that situation up. Now I always try to find a spot where one variable is positive and one variable is negative, so I don't have to worry about negatives at all. And I notice that if I multiply the second equation by 2, what will happen is when I multiply everything in this equation by 2, I get a 2x, 2 times x is 2x, 2 times negative 3y is negative 6y, and 2 times negative 30 is negative 60, and now I do have that positive 2x and negative 2x thing I was hoping to get. So if I can add this equation and this equation together now, negative 2x plus 2x, x's have beautifully canceled out. Positive y and negative 6y, that's equal to negative 5y, and 5 plus negative 60 is negative 55. Divide both sides by this negative 5, and you're going to get y equals 11. And then when I look through these two equations, this one already just has an x, so I won't even have to use any division if I solve for x using that second equation. So x minus 3y equals negative 30. Everywhere I see a y, I'm going to plug in 11. So x minus 3 times 11 equals negative 30. This becomes x minus 33 equals negative 30. Add the 33 to both sides. X equals 3. And then make sure you answer as a coordinate 3, 11. I think we solved this problem a couple days ago using graphing. Exact same problem. And here's an algebraic technique for it. I'm going to show number 2 a second way as well, if you're interested. If you're not interested in seeing this, you might want to fast forward. I have negative 2x plus y equals 5, x minus 3y equals negative 30. So this first time, I tried to take this second equation and make it a 2x in there. But I also noticed that I could multiply this first equation by 3. And that's going to give me a positive 3y here. 3 times negative 2x is negative 6x. 3 times y is positive 3y, and 5 times 3 is 15. When I add the two equations, when I add the two equations here and here and here, the y's will cancel out, the x's will not. I'll be having a negative 5x, a negative 15, and when you divide both sides by the negative 5, you get x equals 3. You then, I'm not going to finish this problem, you then plug it into either one of the equations. I recommend the first one. You solve it out, you're going to get the exact same answer of 3, 11. I just wanted to show that there's some flexibility. There's usually more than one way of using elimination to solve the problem. Final example for the day, number 3. This is what you hope will not happen with these problems, but it will. And in this one, let's take a look. I have 2x minus 3y equals 13, 5x or 3x plus 5y equals negative 9. I don't have the same number in front of these, so I can't add the two equations yet and get any variables to cancel out. So I'm going to, in the same time, I can't multiply one equation by a number and get it to cancel out with the other one. I guess I could multiply this 2 by 1.5, but then I'm going to be getting into ugly decimals, and I don't want to do that. So when you can't multiply one equation by a number, that means you're going to have to multiply both equations by a number. And the advice I give is to look for a positive negative, and I do have a positive negative in front of the y, and because there's a 5 in front of this y, we're going to multiply the first equation by 5, and because there's a 3 in front of the y in this first equation, I'm going to multiply the second equation by 3. What that's going to cause is that's going to cause a negative 15y in the first equation, a positive 15y in the second equation, and now things will cancel out beautifully. So let's see, first equation becomes 10x minus 15y equals 5 times 13. Everybody knows that's 65. That's that first equation. Second equation, 9x plus 15y equals negative 27. And now I do have this positive 15y and negative 15y. You can add the two equations together, 10x plus 9x, 19x. The y's have beautifully canceled out, and Elliot dropped his pen, so he gets another pen. Oh yeah. And when I add up the numbers, 65 minus 27, well, let's see, 65 minus 30 is 35, so minus 27 would be 38. And then when I divide both sides by 19, I do actually get x equals 2. With these problems, you know, if you get a non-fractional answer, I can't guarantee that you're right. When you get a non-fractional answer, it's usually a good indicator that you haven't made a mistake, but it's not a guarantee. And then same thing as everything else. You're going to need to plug this 2 into either one of these two equations. Neither equation looks very friendly to work with. I guess I'm going to pick the second one because it doesn't have a subtraction here. It doesn't really matter. 3x plus 5y equals negative 9. I plug in the 2 for x. 3 times 2 plus 5y equals negative 9. This becomes a 6. subtract that 6 from both sides, becomes a negative 15. Divide by 5, and you end up getting negative 3 for that y value. Don't forget to answer as a coordinate 2 comma negative 3. And oh, so close. Students, I tried to get this lesson done in under 10 minutes. Didn't work out. It took a little bit more than 10 minutes. But either way, if you could do these 3 examples skillfully, you should be good to go with elimination at this point. I'll have some practice problems for you tomorrow. I hope you have yourselves a beautiful evening, and I'll see you tomorrow. Bye-bye. Whoa, 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 whoa. We got to make Elliot big before we say bye-bye. Elliot is big. Bye-bye. Stop.